Did you guys have a chance to print out the note? Oh, you did? Okay, that's good. Okay, that's great. Elizabeth. Okay, so now we're going to start our lesson. Okay. Yeah, drink water. I drink some. Okay. All right. So let's go ahead and start the lesson today. 4.9 Antiderivative. So we're going to talk about antiderivative today. So what's antiderivative? So I look at the Spanish translation and also a Chinese translation for that. So that might be helpful if you speak different language. Okay, so suppose we're given this function, okay, that is 1/3 x cubed, this big F function right here. If I differentiate this with respect to x, what's the derivative of that?
X squared.
Yeah, x squared. Then we'll call this function, this 1/3 x cubed, this function over here, it is an antiderivative of this function. So this function is the derivative of this function, and this is called an antiderivative of this function. So it's go backward. So if you differentiate, you get this, then this is called an antiderivative of this. Now, if I have 1/3 x cubed, the derivative is x squared. But if I put a constant, if I add a constant to that, say I add 3 to that, that will have the same derivative, right? Because the derivative of constant is equal to 0. So this will be another antiderivative of this function, because differentiate that, you get this. So this is another antiderivative of this. In fact, you can add any constant, add any c to this 1/3 x cubed. All of them will have the same derivative. X squared over here will be 1/3 x cubed plus c, where c represents any constant. So that's called the most general antiderivative of this function right here. A formal definition is this, okay? A function, let's call the big F, it's called an antiderivative of the function small f right here on an interval if the derivative of the big F function equal to the small f function for all x in that interval. The most general antiderivative of the function on that interval, you can put that this big F of x at any constant, at any c right here. So c is an arbitrary constant. If you try to visualize it, so you have 1/3 x cubed will be the one that passing this origin. And if you add 1, you shift this graph right here, the pink one up 1 unit, you get this blue graph right here. If you add 2, you shift this pink one up 2 units, you get this orange one right here. If you subtract 1 from x cubed over 3, you get this green one, you shift this down 1 unit. So all of them over here, they are shifted, right, by a constant. So, and all of them will have the same derivative, which is x squared. Those are the members of the family of antiderivative of x squared right here. Okay, right? So they're different by constant. So the next page is page 2 right here. Okay. So look at this example. We're trying to find the most general antiderivative of this function sine x. Now, first of all, let's think about what's the domain. What's the domain for this function? Okay, I'm going to open the chat. If you cannot talk, you can open put it in chat. Domain for this function will be all real number, right? So will be from -infinity to infinity. It's all real number. So what's the most general antiderivative of this function on this domain? Now we need to think on this interval, on this domain. Okay, on -infinity to infinity. What function, when I differentiate, I get sine x? What function, when I differentiate, I get sine x?
Negative cosine x?
Negative cosine.
Yes, negative cosine x. Yes. So we know that cosine x, the derivative is negative sine x. So in order for this to be positive, then we need to make this opposite. So we'll put a negative sign here. Negative times negative positive. Now it becomes positive. The derivative of negative cosine x is positive sine x. So one antiderivative of sine x is negative cosine x. And because we're looking for the most general antiderivative, so we press a constant, an arbitrary constant. Now x to the n. The domain for this will be all real number. when n is positive. Okay. What would be the most general antiderivative x to the n on its domain? So let's think about what function when you differentiate you get x to the n, right? Okay, let's think about that. Now, if I want to get x to the n, then the exponent on this x here had to be, remember when you differentiate, the power is going to go down by 1 when you differentiate. So if I find antiderivative, then I have to increase the power here by 1, increase the exponent here by 1. So exponent here should be n plus 1. Now when you differentiate this, I will have this n plus 1 in front, and then times x to the n. Now, in order to get rid of this multiplication with n plus 1, I need to divide by n plus 1, right? So I'll have this x to the n plus 1. But in order to cancel out with this multiplication with n plus 1, I need to divide by n plus 1. That way, it's going to cancel out with this multiplication with n plus 1, okay? So notice that, so this is one antiderivative of x to the n, because the derivative of that is x to the n. So we put it down here. So it is x to the n plus 1, and then divide by n plus 1, and then add the constant, add c. C is arbitrary constant. Now, the way that you remember this is when you find antiderivative, then the exponent on this x over here is going to increase by 1. So you add 1 to it. So over here, you up 1. So here, you up 1. Exponent here up 1. And then down here, you would divide by the exponent n plus 1. Okay, and don't forget to press c at the end. For example, x to the 5th power. The domain for this will be all real number. So what's the most general antiderivative of this function? X to the what power? X to the 6th power. Increase exponent by 1, and you divide by 6, right? And press c at the end. Okay, now, next one, x to the 1/2 power. The domain for this will be all non-negative number. So for antiderivative here, you increase this exponent by 1, which is going to get to 3/2. And then you divide by the exponent. So you divide by 3/2. Divide by 3/2 is the same as multiply by its reciprocal. So you're going to multiply by 2 over 3 right here. This is a reciprocal of this exponent here. Okay. This next one over here. X to the negative 1/2 power. When you try to find antiderivative, you increase this exponent by 1. Increase by 1, you get 1/2. And then times is reciprocal. Reciprocal for this 1/2 is 2. So you have the 2 in front. And don't forget to press the constant at the end. Press C. So that's how we find antiderivative of x to the n. Now, for all those functions over here, see, this one here, the domain will be all positive number because x is in the denominator. X cannot equal 0. So it has to be all positive number. And also this is a square root. So it has to be all positive number. Now, all those examples that we have above, the domain is one interval. Okay, it's connected. See, one interval, one interval, one interval. It's not disjoint. It's not true disjoint. It's not true separated. Now, the next example here, the domain will be disjoint, like 2 separate intervals. Okay. Now over here, 1 over x. X cannot equal 0. So the domain will be all real number except 0. So it is negative infinity to 0, union 0 to infinity. So you have 2 intervals that they don't connect together. So the 2 disjoint interval right here. Now, how does the graph look like? Okay, let me try to graph this for you. 1 over x, remember our dance move for 1 over x, right? So this is a dance move for 1 over x, like a fan dance, right? The Chinese fan dance over here. So it's like that at the first and the third quadrant. So you see that is a 2 disjoint interval, the domain, all real number except 0. On 0 to infinity, on this over here, what function when you differentiate you get 1 over x? Can you think about one function when you differentiate you get 1 over x? On this is ln, okay? Ln of the absolute value of x. So when you differentiate ln of absolute value x, it is 1 over x. So on this interval, the most general antiderivative will be ln of absolute value of x plus c. I put a c1 over here because it's on this interval. Okay, so plus c1. Okay. Now, similarly, on this interval, from negative infinity to 0, a function that differentiates to get 1 over x is again ln of absolute value of x. So the most general antiderivative of this 1 over x on this interval over here is going to be ln of absolute value of x plus c2, okay, plus another constant. Now, why do you want to put it like this? I put it like this, c1 and c2. That means they don't have to be the same number. So on this interval, you could be plus 1. On this interval, it could be plus 2. They don't have to be the same. So for example, if I have f of x equal to ln of absolute value of x plus 1 on this interval, and then equal to ln of absolute value of x plus 2 on that interval, when you differentiate that piece by piece, remember? So when I differentiate this, I get 1 over x on 0 to infinity. Differentiate this, I also get 1 over x on negative infinity to 0. So the derivative of this function is 1 over x. So they don't have to have the same constant. Okay, when they have two disjoint intervals, you can have two separate constants, two different constants on each interval, right there. So what's the most general antiderivative of the function then? So the most general antiderivative of 1 over x is going to be ln of the absolute value of x plus c1 on this interval, and then ln of absolute value of x plus c2 on this interval. So you can have c1 and c2, two different constants. And when you differentiate that, you will get this. Okay, let's review the derivative first, and then we find antiderivative. Okay, so x to the n, when you differentiate, you get n times x to the n minus 1. Now, antiderivative just go backward. So if you have x to the n, will be the antiderivative of x to the n, where n does not equal negative 1. When n equal negative 1, it is like this one, 1 over x. Then antiderivative will be this. Okay, so in this one, I'm talking about n does not equal negative 1. So what's the most general antiderivative x to the n? We just went over, which is what?
X to the n plus 1 divided by n plus 1.
Yes, we got it. So it's x to the n plus 1. Exponent over here increased by 1, right? So add 1 to the exponent. Now divide by n plus 1. We know the derivative sin x is cosine x. So what's the most general antiderivative? Oh, don't forget to put plus c over here. So all of them, I need to put a plus c. So I put a plus c up here at this. Okay, so all of them plus c. So what's the most general antiderivative of cosine x now? So we go backward, right? So the most general antiderivative of cosine x will be sin x. Cosine x, the derivative is negative sin x. So what's the most general antiderivative of sin x? And you guys just told me before, right? It is negative cosine x. Yes, you got it. And plus c. Okay, so all of this have the plus c right here. Okay, so when you differentiate negative cosine x, so the negative sign will cancel with this negative. So we get positive sin x. Okay, the derivative tangent x is secant square x. What's the most general antiderivative secant square x? So that will be tangent x. You just go backward, right? This is an antiderivative this, and then plus c. Okay, cotangent x, the derivative negative cosecant square x. What about the most general antiderivative of cosecant square x? So we'll have this.
Negative cotangent?
Yes, so we have cotangent x, but to cancel with the negative sign, you need to put a negative right here. You got it. So the derivative secant x is secant x times tangent x. So antiderivative secant x times tangent x will be secant x. So let's just go back. The derivative that is this. So the derivative, so the most general antiderivative of this will be what? We need to have the negative sign, right? Negative, and then what? Cosecant x. Okay, this negative cosecant x here. Okay, what about e to the x? What's the general antiderivative? E to the x?
E to the x.
You got it, e to the x. Okay, press C. Okay, what about a to the x? The derivative a to the x is a to the x times ln of a. So if we just have a to the x, well, the most general antiderivative of a to the x. So you will try to get rid of this modification with ln of a, right? So it will be a to the x itself, similar to e to the x, a to the x itself. But in order to cancel out with the modification over here, you need to divide. So we need to divide by ln of a. So when you differentiate this, you should get back a to the x. Okay, 1 over x. That's the most general antiderivative. That will be ln of absolute value of x. Now remember because the domain here are two disjoint interval, right? Okay, so you can have plus c1 on 0 to infinity, and then we can plus c2 on negative infinity to 0. Okay, you have two different constants. Okay. The derivative inverse sign is 1 over square root of 1 minus x squared. So when you're given 1 over square root of 1 minus x squared, the most general antiderivative will be this, plus a constant. So it's just like going backward, adding a constant. Now, this one over here, inverse tangent, the derivative is 1 over 1 plus x squared. So given 1 over 1 plus x squared, the most general antiderivative will be inverse tangent x plus a constant. Are you able to copy down the note? It's actually important to write down. Sometimes it helps you process the information when you write down. Okay. Now, when you have a constant multiple times of a differentiable function, there will be this constant times the derivative of this function. So when you take antiderivative of a constant times a function, then what happens here is you're going to take the constant also outside. Okay. So you take this constant and then times the antiderivative of this small f function. Let's call that antiderivative big F function. So big F function here. Okay. So this is a constant multiple rule when you take antiderivative. And when you have the sum and difference, okay, either sum or difference. So suppose this is minus. When you differentiate the sum or difference of function, is the sum or difference of the derivative. So over here, then when you find antiderivative of the sum and difference of these two functions, then you will just have the sum or difference of the two antiderivative. So over here, I use the capital F for antiderivative of small f, capital G for antiderivative of small g. Okay, and don't forget the plus constant. Now let's look at this example. We're trying to find all function g such that the derivative g is equal to this, right? Now, this part over here, it doesn't match with the function that we have in the table. We're trying to break it into two separate terms over here, because that way we can write it as power, okay? And then we can use the power rule to find antiderivative. So we have 2x to the 5th divided by x minus square root of x divided by x over here. So we write that term by term. Now after that, you're going to have this 4 sin x plus, okay, dividing this, you'll get 2x to the 4 power, and then minus. Now, square root of x divided by x, okay, is the same as 1 over square root of x. So this is 1 over square root of x. Now, to find antiderivative, okay, of this function, so we better write this in a power form because we can use a power rule, okay? So we're trying to find an antiderivative of this 4 sin x plus 2x to the 4 power minus x to the what power? X to the what power? Negative 1/2. Oh, we haven't taken antiderivative yet. I'm just rewriting this. So this part right here is x to the negative 1/2 power. Okay, so this is x to the negative 1/2 power. Now we find antiderivative. This 4 here is a constant multiple, so you have this 4 right here. Antiderivative of sin x is what?
Cosine x.
Cosine x? Think about the sign. When you differentiate,
Negative.
Yes, when you differentiate cosine x, you have a negative sine x, right? So, but this one doesn't have a negative sign, so we had to put negative cosine x right here. So it is negative cosine x. Okay, done with that one. Now the 2 here is a constant multiple. Just put the 2 here, 2 times. Okay, antiderivative of x to the 4th power is what? You increase exponent here by 1, so that will be x to the what power? The 5th power, right? And then divide by 5. Okay, and then you subtract. Okay, now using the power rule for this one, you increase exponent here by 1. You get this is x to the 1/2 power, and then divide by 1/2, which is the same as multiplied by 2. And don't forget to add a constant, so plus c right here. Now you just need to notice that I'm using the multiple rule, right? So you take this constant in front. Now just need to rewrite this, just simplify a little bit, okay? So this will be negative 4 cosine x, then adding 2 over 5 x to the 5th power. I need to get more space. Okay, x to the 5th power. Okay, and then minus 2 and square root of x, and then add the constant. Okay, so that will be the answer over here. Got it? Okay. So notice that we often use the capital F to represent an antiderivative of the small f. Now, if we begin with f prime, then the antiderivative is this f over here. Okay. So antiderivative of small f is big F, and antiderivative of f prime is f. Okay. And also giving this some actual condition. So we know f of 0 equal negative 2. We try to find this f, the function f. Okay. So given f prime to find f, that means we're trying to find antiderivative. So first we want to rewrite this function f prime over here into a form that's more familiar to us to find antiderivative. E to the x is okay. And then plus 20. You see this one over here to the negative 1 power, negative first power. That means reciprocal. So this is going to be 1 over 1 plus x squared. Okay, right here. Now, once you write it this form, that will kind of remind you for the antiderivative, right? So the general antiderivative is going to be what? What's an antiderivative e to the x?
E to the x.
Yeah, so that will be e to the x itself, and then plus. Now the 20 over here, it is a constant multiple, so just put it like the 20 times. Now, can someone tell me what's an antiderivative 1 over 1 plus x squared?
Tangent x.
You almost you need to fix it. Inverse tangent, right? So inverse tangent of x. So don't forget, it is the inverse tangent of x. When you differentiate, you get 1 over 1 plus x squared. Now finally at the end, don't forget to add a constant, so xc. Now if they don't give you this extra condition right here, then you're done. This is the most general antiderivative. However, they give you this extra condition over here, and they want you to find this function f. Then you have to use this information to find this constant c. So over here, they give you this extra condition over here. Then you need to use that extra condition to find this constant c right here. And how do we do that? Well, you just use this. You plug x equal to 0, and then you get f of 0 equal to negative 2. So let's plug in 0 into x. So plugging 0 into x, this is going to be e to the 0 plus 20 inward tangent of 0, okay, and adding c, okay. What's e to the 0? E to the 0 is what?
1.
E to the 0 is 1, right? Inward tangent of 0, it is 0, right? Inward tangent of 0 is 0. So you get 1 plus 0 plus c, and that's equal -2 because f of 0 equal -2, remember? So you get 1 plus 0 plus c equal to -2. So what does c equal to? Anyone?
-3.
Yeah, you got it. Okay. C is equal to -3. So the particular solution, so once they give you this actual condition right here, you will get a particular solution. Okay. So you put back the c equal -3 there. So that will be e to the x plus 20 and then inward tangent of x minus 3. Yeah. So if they give you actual condition, you need to figure out what c is equal to. You guys got it? Okay. Let's look at the next example. This one over here, they give you the second derivative, and they give you two actual conditions. F of 0 equal 4, F1 equal to 1. So you need to figure out those constants. Okay, use those information. So start with the second derivative, then we can get to the first derivative. So if I take antiderivative of this second derivative, I will get the first derivative, right? So what's the antiderivative this? So you have this 12, right? Exponent on x here increased by 1, so x to the third power, and then divide by that exponent, divide by 3, and then adding 6. Exponent on x over here increased by 1, so x to the second power, and then divide by 2, and now minus 4, and then there should be an x over here. So antiderivative -4 is -4x. And don't forget to add a constant c, like this. Now simplify this, we got 4x cubed plus 3x squared minus 4x, okay, plus c, like this. Now, the antiderivative one more time, okay, we'll get back to the function f, right? So let's find antiderivative this. So again, the constant 4 over here. The power rule says that exponent on the x here increased by 1, so that will be to the 4 power, divided by 4, and then adding this 3 over here times then x here, exponent on x increased by 1, and then divide by the exponent. Now some of you actually, you can skip this step. You can just put x cubed over here. If you recognize the derivative x cubed is 3x squared, you can just go ahead and put x cubed because you see that this is going to cancel out anyway, right? And this is going to cancel out anyway, right? So you can just go ahead and put antiderivative this is x to the 4, antiderivative this is x cubed. You don't have to go through this step right here, okay? Okay, -4x, okay, so minus 4, exponent on x here increased by 1, so x squared, and then divided by 2, so that will be 2x squared, okay? So we can go straight to write down 2x squared. So this is going to be x to the 4 plus x cubed minus 2x squared. Yeah. And the antiderivative of c is going to be cx plus cx. And then don't forget to add another constant. Let's call that d. Okay, d right there. Now, we're given two actual conditions. So you can use those conditions to figure out what those constants here are. So we can figure out what c and d. So we got f of 0 equal to 4 and f1 equal to 1. Okay, let's use f0 equal to 4. Substitute 0 into x. All those terms here become 0. You're left with d. So you get 0 plus d. So 0 plus d is equal to 4. Okay, remember this 4 over here. So therefore, we have d is equal to 4. So we figure out this d. And then we use f1 equal to 1. So substitute 1 here. 1 plus 1 minus 2 plus c plus this 4 right here is equal to 1. So what does c equal to?
-3.
Yeah, -3. C is equal to -3. So we figure that d is 4, c is -3. So this will be, the function here is going to be x to the 4 plus x cubed minus 2x squared minus 3x plus 4. So you have to figure out those constants, c and d. Use those actual conditions. You guys got it? Okay. For example 5, I have made a separate video for example 5. Please watch them later. Now the next one over here, we remember position function. If you differentiate it one time, you get the velocity function. And if you differentiate that one more time, you get the acceleration function. If this object is moving along the straight line, right? Now, what happens if you are given the acceleration Then you can find antiderivative and then find antiderivative again to get back to the position function, right? So you get just reverse it. Okay. So you find antiderivative. So you anti-differentiating once, get this, and then you find antiderivative one more time. Okay. And you will get back the position function, right? Okay. Just reverse it. Now in this example 6 over here, and so a particle move. Okay, now I ask a volunteer. Can someone, Michael, can you read this to the class?
A particle moves in a straight line and has acceleration given by a of t equals 6t plus 4. Its initial velocity is v of 0 is equal to negative 6 centimeters squared, and its initial displacement is s of 0 is equal to 9 centimeters. Find its position at function s of t.
Okay, thank you. So we're given this acceleration, at is 6t plus 4. Okay, so we take antiderivative one time. So we find velocity function. So vt is equal to what? Can someone tell me? 6 over here times t here, exponent increased by 1. So that would be t squared, right? And then over divide by exponent divide by 2, right? And then plus, what's antiderivative for?
4t.
Yeah, you got it. Okay. So that will be 4t. Don't forget to add the constant. So adding c. And then you simplify this. So this will be 3t squared plus 4t plus c. Now we are given this actual condition. We know the initial velocity with 0 is negative 6. So we can use this to find c because this is for the velocity function. This is with 0, velocity at time 0. So substitute 0 into t. So we get 3 times 0 squared plus 4 times 0 plus c on this side. And that's equal to negative 6. Now solving this, what does c equal to?
Negative 6.
Negative 6. You got it. Substitute this negative 6 back to c. We got velocity function is 3t squared plus 4t and then minus 6. That's the velocity function. Now we want to get to the position function. So we take antiderivative this one more time, right? So what's antiderivative of 3 times t squared? So that will be, well, yeah, 3 times t to the third power divided by 3, right? Which is going to be just TQ. Okay, so if you see right away, you can just put down TQ. Okay, and then over here it is, okay, what about 4t? Antiderivative, that will be 4 times t to the second power over 2, right? And if you see the right away, you can just put 2t squared. And now negative 6, antiderivative, that is negative 6t. Again, and don't forget to put a constant plus d right here. Now you need to figure out this d using the actual condition they gave, which is s of 0 equal 9. The initial position is equal to 9. So substitute 0 into t here, you get 0, 0, 0. So you get d. d, and then s of 0 is equal to 9. So you get s of 0 equal to d, which is equal to 9. So we get d equal to 9. Now you put the 9 into d, you get the function, you get the position function. So it will be this, adding 9. So you get pq plus 2t squared minus 6t plus 9. So this is the required position function. Any question? You guys good? Okay, today is a little bit, we have more to cover. I'll try to get it done. Okay, we only have like one or two more pages. Now I would like to ask another volunteer to read this to the class. Do you think you can read this to the class? From
Yes.
here to here? Okay, go ahead.
A ball is thrown upward with a speed of 48 feet per second from the edge of a cliff 432 feet above the ground. Find its height above the ground t seconds later. When does it reach its maximum height? When does it hit the ground?
Perfect. Okay, good job. You did a better job than me. Okay. So over here, I draw this diagram. You know my drawing? The clip. Okay, so I draw this clip right here. So here is a ball. It is it's flow upward. Okay, and the initial speed here is 48 feet per second, and it's going to reach a maximum height here, and then it's going to fall. And the cliff over here is 432 feet above the ground. Find its height above the ground t seconds later, which means you try to find the position function of the ball. So we're going to choose the positive direction. Okay, so we're going to choose the positive direction to be upward. So going up is positive. Going down we consider as negative. So when the speed is going up, so it's positive, and it's going down, it's negative. Okay. Well, what do we know? Remember, we know the gravitational acceleration, right? So gravitational acceleration is 9.8 meter per second square. And in the United States, we use the feet. So it's equivalent to 32 feet per second square. So over here, they're using feet. So for the gravitational acceleration, we're going to use the feet. So we're going to have 32 feet per second square. So AT, it is 32 feet per second square. Now, the gravitational acceleration is pulling it downward, okay, going downward. So we consider going downward as the negative direction over here. So I will put a negative sign in front. So it's negative. So negative 32 feet per second square. Now we're trying to find the position function. So we're going to take antiderivative twice to find that. So let's take antiderivative once. So what does Vt equal to? What's antiderivative negative 32? Negative 32 what? T, right? Negative 32 T.
Negative 32, not 72.
Yeah, negative 32. Oh, did I say 72? Oh, might be my pronunciation. 32. 32. I have a problem to pronounce this 32. Yeah, 32. The TH, I always have a problem with the TH sound. Yeah, negative 32 T. Yeah, like this. And then add a constant right here. Okay. So this will be feet per second, the unit over here. And now we can use this condition that we're given. So we know the initial speed was 48 feet per second. It is positive because going upward. So we can use that to find this constant C over here. So I'm going to substitute 0 into T. We get C. So what does C equal to? So we got V0 equal to 48, right? V0 over here, it is going to be negative 32 times 0, right? Times 0 plus C, right? Plus C. Okay, and that is equal to 48. So what does C equal to?
48.
48.
So C is equal to 48. Now, we put the 48 into C, so that will be negative 32T plus 48. Now we take antiderivative one more time to find the position function. So find antiderivative this is what? Negative 16T squared. So when you differentiate this, you get negative 32T, right? And adding 48. What should I put over here? Antiderivative 48 is what? 48 what?
T.
T. Yeah, 48T. And add a constant D right here. Now over here, you need to figure out this D over here. Using this initial position of 432. So initially, the ball is 432 feet above ground. So using this information to find D, okay? So when you substitute 0 into T over here, what do you get? You get 0 on this part, right? And then plus D. So D is equal to what?
432.
432. Yeah, D is equal to 432. Now you put this back. Then you get the position function is negative 16T squared plus 48. 48t and then plus 132. Okay, maybe I should color code this a little bit. Okay, so this will answer the first question. The height of the ball above ground t seconds later is given by this. So that's the position function. So answer the first question. The second one, when does it reach its maximum height? Well, when you reach the maximum height, if you learn in physics, you know that at this maximum height, the velocity will be equal to 0. Okay, equal to 0 at that time. So Vt, well, we know that Vt is this. We just found out Vt is this. It is negative 32t plus 48, right? This is the one that we found out right here. So Vt equal to 0. If I know the time, then I can find out the height. So I can use this information. So velocity equal to 0 at this moment. You can use that information to find out what will be the t, what will be the time. And then substitute the time into the position function, and we can find the height. So I will set this Vt equal to 0. So substitute 0 here, I get Vt is 0, right? So Vt is 0. Substitute 0 here, I get negative 32t plus 48 equal to 0. So this is negative 32t plus 48 equal to 0. So t is equal to 48 divided by 32. When you simplify, that is 1.5. So 1.5 seconds. So 1.5 seconds later, the object is going to reach the maximum height right here. The maximum height at that moment, did they ask? Oh, they don't ask about the height. They ask about when. So we already answered the question. When the time is 1.5 seconds, then the ball is going to reach its maximum height. Okay. Number 3, when does it hit the ground? When it hit the ground, what will be the position? St will be equal to what?
0?
Yeah, equal to 0. So when it hit the ground, St will be equal to 0. And we know St, right? St, we already found out, was given by this, negative 16t squared plus 48t plus 432. So you're going to set St equal to 0. Then you get negative 16t squared plus 48t plus 432 equal to 0. Now you can solve this equation, but it might be easier for you to divide by negative 16 on both sides first. Then divide by negative 16 on both sides, you get t squared minus 3t, and then minus 27. Now to solve this quadratic equation, I tried already. I couldn't solve this by trial and error, so I use a quadratic formula. So use the quadratic formula over here. I get t equal to this. I'm going to discard the negative one because time cannot be negative right here. So I only take the positive one. So this is the exact answer. And I find a decimal approximation to this exact answer here, which is about 6.9. So 6.9 seconds, about 6.9 seconds later, the ball is going to hit the ground. Okay, so let's see. Do you guys have questions about this? So here's the graph for the position function. So the ball is going to go up and then later on decrease as we hit the ground over here. So this is about 6.9 seconds at this time. Okay, now we're done with the lesson. Are you guys okay?